I'm going to name just a few biological terms you most likely heard and maybe memorized definitions for before that you really need organic chemistry to understand what they're doing. It's the old structure function relationship, right? And that structure is an organic structure. It can be understood with concepts of organic chemistry. So thinking back to maybe bio 6 or high school biology, whatever your last bio class was, think about these terms and if you have an idea of what they mean. Fats, fatty acids, waxes, vitamins, steroids. You know what they all have in common? They are all in the category called lipids. Very broad category. So what does it mean to be a lipid? You'll see it's a broad definition, but it's an organic molecule, what I was getting at. So organic molecule of biological origin that is insoluble in water. So water insoluble. And that's significant because the body's aqueous. So that dictates a lot of how we classify things. That is water insoluble and is therefore soluble in organic solvents. So of course we don't pour benzene in our body, but if we were to study them and react them to understand them better, we could use an organic solvent to solubilize them. Which says a lot about that. That means they tend to be less polar because they have lots of hydrocarbon character to it. So in this big family of biologically relevant organic molecules that are hydrophobic, that's a shorter way to put that definition, we will be studying specifically what makes something a fatty acid, a wax, a triacylglycerol, a fat, phospholipids, eicosanoids, and specifically we'll look at the prostaglandins, terpenes, steroids, and lipophilic vitamins. So not all vitamins are lipids, but the ones that are classified as lipids are going to be discussed here, and we'll point that out. So that will be our focus. So we'll the structure of this next section is to break these down one by one and understand the organic structure of each of them, and that will help us understand more what it's doing for its function biologically. So let's start from the top. Fatty acids. Probably heard that term a lot, but think about that as an organic chemist now. Acid. You need an acidic functional group. And when we just say the word acid, it has an acid on there, we're talking about the carboxylic acid. So fatty. What does fatty mean in organic context? Fatty means greasy. And I'm not talking about what you're thinking about in a big scale. I'm thinking about we've described molecules as greasy before. That means they have a lot of hydrocarbon, like a long hydrocarbon chain. That makes something greasy. And there's someone that wants to join our lecture again. Excuse me. Sir Buckminster Fullering, Albert, you may join us. Speaking of lipids, he's on a diet. It's hard for me to even lift him up. I know, I'm sorry, that was insulting. There we go. He's not too happy about that. Okay. May I continue? Or are you going to chew on my microphone wire? Okay. Thank you. Back to our fatty acids. Fatty, greasy hydrocarbon. Acid means we have a carboxylic acid. So we'll see a lot of CO2H, or maybe we'll draw out the Lewis structure. Okay, so in other words, it contains, let's fill that in, an unbranched chain of carbons. There's your hydrocarbon chain with one carboxylic acid. So these are produced naturally. So the biosynthesis involves the addition of 2 carbons at a time. So the vast majority of them will have even numbers of carbon atoms. The most common that we will see has 12 to 20. But the most important one that we're going to use as a starting point in understanding a lot of other molecules as its derivative is the one with 18 carbons. We'll work our way to that one. So fatty acids further break down into 2 major categories. So if there are absolutely so imagine this long chain of carbon atoms, and if that long chain of carbon atoms has absolutely no pi bonds, so that would mean every carbon has the maximum number of hydrogens it could have, aka it's saturated. However, if it has 1 or more pi bond, that's a degree of unsaturation. Therefore, it's unsaturated. Brings a whole new meaning to saturated fats, unsaturated fatty acids, right? Okay, so their biological role is that they are usually a component of other lipids. So fatty acids are attached to something else to make it a fat. But they're, we'll look at that structure before we make that attachment. Okay, so some really common saturated fatty acids, starting with carbon 12, are listed here. And then as you could see, so there's the greasy hydrophobic chain and the polar end group that is the acidic functional group that can allow it to attach to something. So I'm going to try to, sorry, this is freezing on me. Here we go. There we go. All right, so here's my carboxylic acid. And this is my greasy, nonpolar, fatty chain. Lauric acid is actually found in coconut oil, by the way. Something just to note with these, we have the potential for their neighbors to to stack and have additional van der Waals forces. So when lauric acid sees another lauric acid, it can nestle into its chain very nicely and make like a sort of a nesting set that stacks. And when you remember going way back to intermolecular forces, when you stack a lot of surface area between molecules, that increases their intermolecular forces. So I'm going to write this as we go. So that linear shape that you see facilitates more van der Waals forces, more surface area. For increased surface area for increased van der Waals forces. What does that consequence have on its bulk properties? Remember, as you increase intermolecular forces, you increase melting point. As you increase melting point, then it's less likely to be a liquid at the temperatures we're thinking about biomolecules now. So now we're not thinking about the extremes of what we work with in the lab. We're thinking about our body temperature, or maybe what we have at room temperature, or variations in weather. So if you've ever, there's a lot of chemistry and cooking, right? And so if you've ever used coconut oil, you might have noticed when it's in a jar, it's kind of in between, but it's actually mostly solid most of the time. And because it's saturated, and that allows it to stack and nest with its neighboring fatty acids. And when you do that, you increase the melting point, which means it's more likely to be solid at room temperature. Why are some other options for fats in our diet liquid at room temperature, like olive oil? That's because they are these so-called unsaturated fatty acids. The degree of unsaturation is introduced with the pi bond. Yes, they all have a carboxylic acid. We're talking about the chain only. So the fatty side chain, if it has no DUN, if a DUN of 0, it's saturated. But if there's even one pi bond, it's now unsaturated. And alkenes are actually usually cis in this case because they're biologically produced. So an enzyme conformation dictates the stereochemistry. So they're cis, even though trans, if we were to do it in a flask, would have been more stable. But notice what the cis bond does. Let's look at oleic acid, for example, which is one that's found in olive oil, also peanut oil. Look at this cis bond. It introduces this kink in the ring. There's that bend. That bend makes it more difficult for it to tightly pack with a neighbor. So we'll draw those same conclusions. Less packing for van der Waals forces. Less van der Waals interactions means a lower melting point. Lower melting point means it's more likely to be liquid at room temperature. So, however, because trans is more stable than cis due to those interactions, it's fairly easy to isomerize these cis fatty acids into trans. How do you do that? So we're talking about the unsaturated fatty acids here. But let's suppose we do this. I'm going to add some heat. When I add heat, when I'm cooking, let's say I say, oh, olive oil is so much healthier than coconut oil or animal fat, which has a lot of the saturated fatty acids. So I'm going to use olive oil for deep frying, and because I need to have my French fries. And by the way, this isn't a guilt trip. I still like them, but it's just nice to know the science behind it. So you put in the, you heat up your oil, ready to the temperature needed to deep fry. And what does the heat do? It isomerizes this bond, the cis, to the trans. Because thermodynamically, trans is more stable. We access the thermodynamic structure by adding heat. So let's, so OH there. And we have, how many down is that? 1, 2, 3, 4, 5, 6, 7, 8, 9 on the 10th carbon from the carboxylic acid. So we have 2, 4, 6, 8, and 10. And on the 10th carbon, it would have started there, but it isomerizes to trans. And I'm just going to draw a squiggle line so you don't have to draw the entire rest of it into those words. But now look at what happens when we have the trans. We still have an unsaturated fatty acid, which makes up the fats. However, the unsaturated fatty acid is no longer bent with that cis conformation. It looks a lot more like these linear cases up above. So this is what, so now that this is trans, this is the component in trans fats. Trans fats are not naturally occurring. And so I suppose that's why they're considered the worst of all. So ideally you have the unsaturated fat because you want the liquid at room temperature. Why is that? Because if you're consuming something that's not solubilized and in aqueous solutions and it stays solid at high temperatures, then what is it going to do to your arteries, right? So once it gets in there, it stays, it might melt here and there and dissolve a little bit, but then to redeposit and build up the plaque. So if it's always a liquid, that's much better for cardiovascular health. If it's a trans fat, it will once again be a solid at room temperature, right? So because it has that linear shape, so then it's going to be solid at room temperature. The trans fat is apparently even worse simply because it's not naturally occurring, so your body just encounters more obstacles with metabolizing it And that's a complex situation that might not be fully understood. But so naturally occurring usually wins out over non-naturally occurring in terms of diet. So that's not a naturally occurring fat. So it's ideal if you can avoid that isomerization or the sometimes decomposition of the fat. So, that's something to keep in mind. Okay, one of the really popular ones we'll see in a minute is arachidonic acid, 20 carbons. Look at all of those benzene in there. It's actually a popular starting material we'll use later. There's linoleic and linolenic acid. These are all 18 carbons, but they're isomers of each other. They have different degrees of unsaturation. Okay, so what you want to know is that you can identify a fatty acid and tell whether it's saturated, unsaturated, trans, cis, that sort of thing, okay? All right, so next category, waxes. Like beeswax, right? Okay, so structurally, where do waxes come from? So here's beeswax right here. And so look at that, 23 carbons in the parentheses, another 28 on the other side. I mean, greasy, but somewhere along the line, there was a fatty acid involved. But we made an ester, so it's an ester, okay? So waxes are esters, not carboxylic acid. How do we make esters? We know how to make esters. How do we make an ester? We start with a fatty acid. So that's a fatty chain right there. But when we make esters, we start with the carboxylic acid. So biologically speaking, we'll use a fatty acid. And then we use a long chain alcohol to get that long chain. But alcohol plus acid is basically like a Fischer esterification, right? So we've done that theoretically. So likewise, waxes are derived from the fatty acids and a long chain alcohol. To make that ester. Notice that while we have a few polar bonds in there, we have the carbonyl and the CO bonds, that's it. If someone asked you to describe this molecule as polar or nonpolar, you got to pick one. It's got to be on one side of that. Yes, they may have polar components or nonpolar components, but we've got to pick which side of the fence it's on. We're definitely going to call this nonpolar because look at this, definitely all overwhelms the small contribution to these few atoms that have polar bonds. So we know that to be true because wax is very hydrophobic. So it must be nonpolar, right? That fact that it's very hydrophobic, I mean, incredibly high number of carbons and hydrogens, allows it to be a wonderful water barrier. So not only is it commonly found biologically as beeswax, but there's also waxes identified, those esters in that form, for feathers, coating feathers like water off a duck's back. You heard that term? Because they can dive under and they come up looking like they're dry because they have that waxy hydrophobic coating. Leaves, if you've ever put water droplets on some leaves, you'll notice what's called the contact angle of the water droplet. It stays roughly spherical because it's repelled by the wax on the leaf and just rolls off, as opposed to something that would be hydrophilic. The water contact angle would be bigger and flatten out. That's why those who have nice cars bother to wax their car. Keeps the water out to maintain the paint job for much longer. Okay, so if you wanted to study the beeswax, you could hydrolyze it. You could identify its component alcohols and acid. So what you want to be able to do is draw the forward and reverse direction. So if you were given two alcohols, and this is basically saying do a Fischer esterification on a biological set of provided alcohols or fatty acids. So you want to be able to actually predict how it would hydrolyze. So if you saw the ester, what alcohol and what acid it came from, or predict how they would form that bond. So if you've given the alcohol and the acid, how it would form that ester. Glycerol will be a common linking triol for us. So the sooner we get comfortable with it, the better. So I'm going to draw out glycerol. 3 carbons, 3 alcohols. Every carbon has an OH. One, two, three. Glycerol. Now you just did a Fischer esterification type reaction to make the wax. If we have 3 alcohols instead of 1, we need 3 acids to do another esterification. Let's do 3. Fatty acids. What do we get? Army with harmony. We get a triester. So that gets its own category because that's different than beeswax. It has different properties than beeswax, which is a single ester. Okay, the esters don't have to be the same. The R groups can be different. Okay, so we get a triester. That triester is the triacylglycerol. That specific triester. So let's fill in the blanks here. Triester derivative from glycerol, right there, and 3 fatty acids. Okay, so this is where we use the fat. Like I said, fatty acids keep coming up as a component of other lipids. They themselves are not the fats. They make fats. So what is a fat? A fat is when we have a solid at room temperature, but it's also this triester. So when the fatty acids are attached to glycerol, it is a fat if we had most of those R groups were unsaturated or trans and allowed a lot of packing, then it's a fat. If they are unsaturated and, unsaturated with those cis bonds, then they're most likely a liquid at room temperature. So then they'd be an oil. So we get the fat versus the oil. So let's put fat in blue and oil in green. And oil in green, I'll put if R equals unsaturated, saturated fatty acids. Most likely. It could be a mix and match, and then that'd be hard to predict. But if they're made of saturated fat, saturated fatty acids, then we will have a fat. So there's your fat. The fat's that triester with the 3 fatty acids attached, such that they are made up to have a high melting point. Okay, so once again, the melting point of a triacylglycerol, dictating whether it's a fat or oil, will increase with a larger number of carbon atoms in the fatty acid side chain. It will also decrease, have a smaller melting point, increase with a smaller number of alkenes, because the alkenes are cis, they add that bend in the ring. We know that we use fats for energy storage, right? So that's their main role. But let's look at a couple. So just to give, let's take the fat, an animal fat versus a plant fat. So from butter, I've got the structure that's most commonly found in butter fat. versus a lot of the plant oils. So that is commonly found. And notice that the R groups are not all the same. Notice the butterfat has an unsaturated fatty acid in there. So you can mix and match. But notice that because it has a long number of carbon chains and 2 of the 3 are saturated, butter is actually, it's at room temperature, it's it's a soft solid. So you can probably thank that cis pi bond for that. It's not as hard. Now think about plant oil. Notice that's just those small changes in the plant. Some of the popular plant oils like olive or sunflower oil, peanut oil, that introduces a number of degrees of unsaturation, less packing, and keeps it oil. Still has a lot of calories. It's a matter of how it helps with the cardiovascular health with the storage. Okay. So if we were to, so we showed how they come together. If we were to hydrolyze it, that's how they come apart. We get glycerol back. And in fact, this is done quite regularly. Actually, in the old days, your ancestors would save their fat. Like they'd fry up some bacon. They wouldn't throw away that fat that comes off, that you can scrape off. It is oil if you leave it in the pan long enough. They would save that in a jar by the stove. Then, so that would be their triacylglycerol. Then they would actually intentionally add a source of base, which they would get from lye, which is where it's produced from taking the ashes, which have a lot of that are very alkaline, very basic, and making a solution from them. So adding ashes to, so basically all the things we throw away now, we throw away. If we have any fat that we made from cooking, we throw that away. If we have any ashes from a fire in a fireplace or fire pit, we throw that away. They save those to make soap because that would hydrolyze this ester. And specifically, this reaction is called saponification. Now, just hydrolyzing an ester under basic conditions is saponification, but this is the OG saponification reaction because sapos is soap, and it is the soap-forming reaction. Okay, so in other words, you get these guys back out. This is the conjugate base of the fatty acids. And usually we get the lye from the ash. So that's how our ancestors would make soap. And we're going to get into the chemistry of soap a little bit because it relies on lipids. So you want to, before we get into this hydrolysis product, be comfortable with triacylglycerols. Know the structure of glycerol because you'll want to draw regularly a triacylglycerol the forward and reverse direction. Okay. Now let's take a closer look at this hydrolysis product here. The conjugate base of fatty acids. We're going to hone in on that right there. All right. So let's say we have this fatty acid. This is the one found in like beef fat, for example. Notice it's very highly saturated. Notice we have our polar N group, but the rest of it is very greasy. And so the reason this is so useful to serve what we use soaps for is because I'm going to make a little cartoon of this non-polar part, the tail. So this is the non-polar fatty chain, and this is our polar carboxylate. So the carboxylic acid is already polar, but the fact that you've deprotonated it or kept it deprotonated makes it an even more polar because it's ionized now, right? An ionic bond is significantly more water soluble than just a polar bond. So this is water soluble. So we have an H2O soluble head. We have a hydrophobic tail. And when we use soap, the reason this is so helpful is because water is what we wash it off with. Water is our universal solvent. So when we wash off the soap, it needs to come off with the dirt. The dirt is almost always organic material, which means it's nonpolar. What is dirt? Dirt is remnants of animal and plant material, therefore all organic compounds. So, if your hands are particularly greasy, that's a greasy hydrocarbon chain. So you need grease to get grease off. So thankfully soap has a grease and it has a part that will solubilize the grease, because that without the polar head, then it would just be more grease on your hands. But because you have the greasy part, it interacts with the dirt, the like interacts with like, the tails all orient like little soldiers, all lined up around the dirt particle or virus particle, right? You didn't like that. I know, nobody does. The polar head is there to interact with the water. The water will be very attracted to that. Because we know water is polar and it's hydrophilic. That carboxylate is hydrophilic. So the result is it lifts the dirt up off your hand, and any exposed dirt gets clustered immediately by more greasy tails. So they don't like to be, they're all facing inward because they don't like the water surrounding them. So there's water washing off your hands or whatever else you're washing, and the dirt is, and the greasy hydrophobic tail is facing inward to avoid the water. So it makes this little capsule called a micelle. So luckily, because that water capsule is hydrophilic on the outside, the water will wash away that capsule that is hydrophobic on the inside. That's what makes soap so useful, is that dual sort of nature of it. Now, if you go, actually, I want you to take a break and go find some soap in that might not be opened yet, and just read the label. You might see one of the most common ones is sodium lauryl sulfate. And we talked about lauric acid, right? You might even see, so sulfates are a common modification of the carboxylate. Or you might even see, if you look up the structure, a group that's not part of a fatty acid that we've learned. So most soaps have been synthetically modified these days. If we go to the store and buy a soap, they're usually not derived straight from beef fat. They're synthetically mimicking natural fatty acids. So why are they synthetically different? So turns out that with other things we need to have a household running smoothly, like water, tap water, irrigation, a lot of people have hard water. Hard water means there's a lot of metal ions in it. And naturally made soaps from fat, animal fat, and lye have been found to be insoluble with hard water. Hard water, those metal ions tend to keep it precipitating out. So it's less effective as a soap, and also could cause issues with, pipes getting clogged and everything. So the synthetic modifications are made to emulsify that better and, increase solubility with hard water. So I'll write that out. Increase solubility in hard water. So hard water, that means you have metal cations present, like magnesium, iron, calcium. Okay. Okay, so Related to the function of soap, we have phospholipids. Because you've heard of that hydrophobic tail, hydrophilic head, phospholipids are very similar. So it makes sense to cover those next. Okay, so phospholipids. I'm going to go into the most important type because we are not, there's a huge area of molecules we could be talking about. We're going to kind of hone in on the most discussed ones, most studied ones, and then, you know, if you understand that one, you can probably transfer this concept to other specific types. But if we have a glycerol unit, so that's the triol, 3 carbons, 3 alcohols, and it has 2 fatty acids, and 1 of the alcohols is instead occupied by a phosphate group. So it's basically like you take a fat and you replace 1 of the fatty acids. So, oh, look at this. This is missing that ester. I think that's from that same structure I had drawn earlier. I gotta go track down that source. That's an O. Add that O in there. You see that? Because this came from glycerol. Glycerol right here. Remember, that's kind of our stem alcohol. So if you were going to look for glycerol, you should see 3 O's coming off the 3 carbons, 1, 2, 3. That's how I spotted that O. That was very obviously missing. So these come from the fatty acids. Okay, so glycerol there, fatty acids. If this last one had a red circle like this one, this would be a fat. So instead of being a fat, we have this other new group here, this phosphate group, ionic group, very polar. So ionic polar head. So we're going to represent it just like we did with the soap for the micelles, the polar head and the nonpolar tail, but this time it'll be nonpolar tails because we have the 2 fatty acid chains. So the cartoon representation that you've probably seen many times for a phospholipid is to have the, you know, sort of, let's do some coloring. Whee. That's kind of relaxing, right? Some adults. We need an adult coloring activity. There we go. Okay, so that's our ionic head. And then our glycerol is connecting it. I could just make a little blue there, right, to these tails. Now, that did it for me, but you could always color that in if you really want to. But you can imagine, so these come together like attracted to like, just like in a micelle fashion, except this forms the bilayer instead of the sphere. So all of these like pieces that are polar stick together, water soluble, water insoluble, hydrophobic. Okay. So then we get that nature, that dual nature. There's a word for that, right? If it's hydrophilic and hydrophobic in the same one, we call it amphiphilic. It likes both hydrophobic and hydrophilic environments. That's what makes it a semi-permeable membrane, right? So that's the function, permeable membrane. Okay, so very important features, right? Cell membranes. What you need to do, structurally speaking, as an organic chemist studying this aspect of biology, this isn't a biology class, we're not going to be concerned with what makes it semi-permeable after that, what passes through. We're sticking to the structure. So you want to, if you see a structure, you need to know, is that a phospholipid or not? Okay. And then draw one, maybe given it's R groups. So if you're given R groups, can you sit down and draw a phospholipid? Okay, so pretty still structure based here. Eicosanoids. It's our next category. We're checking down the list. Check, check, check. We're getting near the end, actually. This one's pretty cool. Now, a fatty acid that we mentioned earlier has 20 carbon atoms is going to be brought back to center stage to discuss this one. Arachidonic acid. So that's a large number of carbons, but it's also one of the, it's found in peanut oil, which indicates it's probably saturated or unsaturated. So most people say do that plant-based diet thing because we get less saturated fatty acids in the fats. So because it's from peanut oil, it's a good guess that it's probably got a lot of unsaturated components to it. So go back and look at that structure. Okay, so arachidonic acid, we'll see it again. The most important eicosanoid. There's a lot of them, but we're only going to really focus on one, and that's the prostaglandins. So this is a subcategory of eicosanoids. So eicosanoids are molecules derived from arachidonic acid, clearly an important fatty acid. And then within that broad category, we're going to look at strictly prostaglandins, which have this skeletal structure that is, we will explain how it's derived from arachidonic acid. Yes, it is, because it has the same number of carbon atoms. The prostanoic acid skeleton. So the skeleton, that means there could be modifications to the skeleton, but as long as it has this number of carbon atoms, then, so count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 carbon atoms. Furthermore, you have that 5-membered ring and you still have the carboxylic acid. So that's the prostanoic acid skeleton. In fact, we're going to be trying to identify it in a more complex molecule and spotting them. So you might want to, I'm gonna make that a little skinnier. You might want to be ready to maybe even highlight it in something so you can spot it. So I'm using a highlighter here. So this is the prostanoic acid skeleton. There might be methyls coming off, alcohols coming off, pi bonds added in, but you still want to have that basic skeleton to be able to call it a prostaglandin. So why is it called a prostaglandin or prostanoic acid skeleton? It's because these are found in the prostate. Actually, they're found throughout the body, but they were first discovered in the prostate gland. Let me go back to pen. So the history of that is discovered in the prostate gland. So presumably those scientists at the time said, okay, well, this is something that's part of the prostate, so we got to call it part of the prostate gland, so we got to call it prostaglandin. But since then, they've been found throughout the body as well. What roles do they serve? Some very important roles, but a lot actually. They give signaling for constriction and dilation of muscles, platelets, whether they aggregate or disaggregate, hormone regulation, and cell growth. Let's see how they are made in the body and how they are derived. Like this is arachidonic acid, by the way, just to remind you. And it's been, it's usually a long chain, but it's been wrapped back around so that you can visualize how it closes up to a ring. But other than that, it's hard to see how those are really related other than the fact that they both have 20 carbons. So let's check it out. All right, so here's a synthetic scheme, which is refreshing to see. We don't see as many of those here, but we do have reactions to do. Here's a synthetic scheme that shows exactly how we get to 2 different prostaglandins from the same starting material. Prostaglandin E2, prostaglandin F2 alpha. Creative names, right? First of all, before we even look at how that was made, can we recognize, if you saw this structure, prostaglandin E2, would you know that was a prostaglandin? Yes, because it has the prostanoic acid skeleton. If you need to count carbons, you can, but I won't force you to watch me do that. But we look for 20 carbons that have a carboxylic acid, and in the middle have that 5-membered ring, and then the other chain making up the rest of the 20 down below. So yes, there was an extraneous ketone and 2 alcohols, and there's stereocenters at play. We're still, it doesn't matter. Those modifications don't take away from the fact that it's a prostaglandin. Here's another one. Look at how different it is. There's no ketone. There's alcohols instead. But once again, we can highlight. Doesn't matter whether there's pi bonds or not. We can highlight 20 carbons where there's a carboxylic acid, then 1, 2, 3, 4, 5, 6 carbons, then a 5-membered ring, then the remaining carbons on the chain below, adjacent to it, right? Okay, so how is this made? Arachidonic acid reacts with the enzyme, and look at the name of this enzyme. And we're not given a structure of the enzyme because it's enormous. Enzymes are huge. Their active sites are very interesting, and we'll look at that later. But the active sites explain everything, where it fits in, and then all the chemistry happens there. The rest of the enzyme doesn't necessarily play a role. But very specific enzymes are often named after their function. Cyclooxygenase. Well, let's see if we can see what changed. From here to here, we made a ring, and we added bonds to oxygen, hence the cyclooxygenase. And the ACE is a suffix commonly used for enzymes to let you know that you're dealing with an enzyme. So cyclooxygenase 2 allows us to close this ring here and insert 2 oxygen, a peroxy group. This is called prostaglandin H2. It's still a prostaglandin. It doesn't look like one as much, but look, we have that 5-membered ring right here. And then we have that chain down there. So even though it's a squished looking 5-membered ring with a bridge, it's still a 5-membered ring. All right. Prostaglandin H2 can further react to make 2 other types of prostaglandins. It depends on the enzyme it encounters. PGH-PGE isomerase, PGH-PGF2-alpha reductase. Wow. What does that mean? We have, if you look at the number of bonds to the oxygen, we have an oxygen-oxygen bond, a carbon-oxygen, and a carbon-oxygen, right? And so instead of having this oxygen-oxygen bond, we get the oxygen-carbon bond twice right here in the isomerase variation. Whereas here we lose the oxygen-oxygen bond and we don't replace it with an additional bond to oxygen, hence the saying that it's been reduced, right? So we lost, usually we define it as bonds to carbon, oxygen bonds to carbon, but it also includes bonds to oxygen. So since oxygen is not bound twice, we count that as a reduced, an overall reducing effect. So yeah, once again, the enzyme describes it, but I wouldn't, I could reduce a number of things here. So you'd have to kind of know what's going on. You don't have to memorize enzymes, but maybe just kind of follow the path. I mean, in fact, what you really need to know how to do is listed here. If something's an eicosanoid, and the only eicosanoid, how convenient that you have to know is the prostaglandin. So if something's a prostaglandin, it's an eicosanoid. Now, anything else derived from arachidonic acid is also an eicosanoid for future reference, but the only ones we're covering is prostaglandins. Now, you should be able to find a prostaglandin in a complicated molecule like these, find their skeleton. And to do that, it's a good idea just to practice drawing that skeleton a lot of times. Okay, these might be my favorite, terpenes. You'll see why soon, but I think it's fun to find out why they're a terpene. It's like a little sort of investigation puzzle you got to start to do. So what makes something a terpene is that they are composed entirely of repeating 5-carbon, oops, this is definitely not use yellow, 5 carbon units called isoprene. Notice the word or the prefix iso. Don't worry about isoprene. Isoprene itself is a molecule, but you have to have, if you were to shape the skeletal structure of it, it's basically this isopentyl group, right? Because that isopentyl group often has a pi bond, you'll hear the -ene suffix, isoprene, but it doesn't have to. It can have no pi bond. But if you're able to circle the isopentyl group, you have circled an isoprene unit. So it may or may not have pi bonds. So for example, if you find this piece in a molecule, you can circle that. That's an isoprene unit. It may only have 1 pi bond. It may have no pi bonds. Those are all isoprene units. Okay, so why are isoprene units so important? They are the synthetic building blocks of terpenes. So you can, if you know something's a terpene, you can circle where all the isoprene units are connected. So it might have 6 isoprene units connected head to head, tail to tail. So while we're at it, let's label that. This is the head. This is the tail. So the head has the branching. So just kind of do that. So head to head, tail to tail, or head to tail. How are they made? If you start with, we're not going to go into the complete biosynthesis, save that for biochemistry, but if you start with acetyl-CoA and lots of enzymatic steps later, you get something that you could use as your synthetic starting points with an isoprene unit. So let's circle it again. We're going to be circling those regularly. So you find 5 carbons with an iso group. If you need to label or count, go ahead and do it. There's your isoprene unit. But then you have this attached. You need some functionality to get the N group on there. So you have to ask yourself a very important question. Are you down with OPP? Are you down with O pyrophosphate? O pyrophosphate. That's what that song was about. O pyrophosphate, OPP, when you draw it out, has that structure. What is important to know about the structure? Imagine this breaking and leaving the lone pair here. It's highly resonance stabilized, meaning it's a great leaving group. It's nature's leaving group. So we can follow arrow pushing because electrons still flow, even if an enzyme is largely controlling the process. You have to have electron flow, and you can make some predictions and still do a lot of arrow pushing, even if it's a biochemical synthesis. So I will demonstrate that with the synthesis of a terpene. So we can start with one of those 2, for example, starting materials, and I'm going to use those and show how a very well-known terpene, limonene, which is found in citrus fruits, and that's responsible for that nice smell. Terpenes, one of the reasons they're my favorite is they have a wonderful smell too. They're abundantly found in those essential oils. Cinnamon alone has several different versions, so you can find isoprene units connected in very interesting ways to make an abundant array of terpenes. Okay, so let's look at one natural oil that's also nicely smelling, is limonene. And we are going to show how it can be synthesized. We'll do our best to push some arrows, in other words. I'm going to once again circle those. You want to get, when you're talking terpenes, you're looking for isoprene units to prove it. So if this is the isoprene unit and we're saying this is a terpene, that means you better find isoprene units to connect all the carbons. Every carbon's connected in a way that goes back to an isoprene unit. So I always start with a very obvious branching point for the iso group right here, right? And then you got to go in there and say, okay, well, where I have 3 carbons here. Where do I get my next 2? Sometimes it's trial and error because you'll get stuck sometimes running into the other guy's isoprene unit. So this is 1, 2, 3. Ooh, I caught myself. 4, 5. I circled too many. So I'm going to erase that last one. That's why it pays to count. Can't circle 6. Now let's circle another one. The leftover carbons better be an isoprene unit or we don't have a terpene. So notice when I have that same like Y shape for the iso group and then the tail. So here's the head of this one. And here's the head of this one. So you would want to, if you're told something, is a naturally occurring molecule and you're asked to classify it, you would need to be able to look at limonene and say that's a terpene because I see isoprene units. You need to circle the isoprene units. Then we're going to talk about how they connected. Was it head to head to tail, and those are the 2 orientations, together or on the side. So notice that the head and the tail are offset. So the head is here. Here's the tail. So the tail of one is next to the head of the other. So head to tail arrangement. Okay, so let's push some arrows. Knowing that OPP is a great leaving group, then we can let it leave. 1, 2, 3, 4, 5. Okay. Still there. Still got our 5 carbons. I didn't lose that. I just had the leaving group. I'm missing my pi bond though. So I have a primary carbocation, however, resonance stabilized. So I can indicate that as usual. So show the resonance stabilization. Oh, nice tertiary carbocation. That's also resonance stabilized. Okay, along comes the other one, which, remember, this is actually a 211 style reaction. Just as we can add to pi bonds, we could use them as nucleophiles. So it can attack here, right? The carbocation. So let's show that. I'm going to actually number these, because this is carbon. Let's call it 6, 7, 8, 9, 10, because now they got to make a bond and make a big long chain. Okay, so let's number 1, 2, 3, 4, 5. Here comes the new bond. So I still have the pi bond there. New bond, 5 bonded to 6 or 7. Well, if it bonds to 7, we get a tertiary carbocation. Sounds good to me. And it also gets us closer to our structure, as we could see. So you could think of a lot of other outcomes, but you want to make the one that's going to produce limonene. 7. 7 is attached to 6 and 8, and 6 is also attached to 8. So 6, 8. 6 is also attached to 9. That's where that iso group comes in. And then finally 9 is attached to 10. And we still have the other OPP waiting to play a role because it doesn't make it into the final product since it's a leaving group. Okay, what happened to my pi bond? My pi bond attacks, so 6 is now a carbocation. Okay, I'm gonna make a little space. All right, so notice in my final product, I have to do a cyclic attack, and I don't want to do that yet because I need a second pi bond. I have 2 pi bonds there. So I'm going to eliminate. I notice that the pi bonds are part of the iso group. right? So iso, iso. So I'm going to eliminate this H so that I can get the pi bond toward the iso group. So something that could act as a base with its lone pair, with an E2 style, or I guess it's E1 because we've already formed the carbocation. Okay, so after we do this elimination, we would have a pi bond there. Let's start to draw that out. And catch me when I do something strange. Okay, so I'm going to actually number these two. 1, 2, 3, 4, 5. 7 was the new bond from before, not anymore, we're making the pi bond. 7 is also bound to 6. 6 is bound to 8. 6 is also bound to 9. Nine is bound to 10, which has OPP still, its own OPP. And I made the pi bond that way. Notice what I did there? I rotated 10 down. And cis is the preferred conformation. That's because the enzyme controls that. Enzyme controls the stereoselectivity. Why do we need cis? It's going to be in a ring. If it's going to be in a ring, we need to have a cis pi bond. Or I should say, technically, we tried this as Z, right? Because there's not a hydrogen there. Okay, now that we have, that's the only step that looks like waving my hand saying the enzyme did it without showing how. You'd have to increase the complexity of this problem a lot and look at the active site and why it was able to do that. Which is interesting, of course. That's where biochem realm takes over organic realm. All right, so now let's do the ring closing. We're going to prompt the ring closing by letting OPP leave. There it goes. And then when it leaves, we will have a resonance stabilized carbocation, which is why it was nice, by the way, that we went ahead and did that elimination for this next, so that we're set up for this next step. Now we can close onto that primary carbocation. And we got to count. Remember, every time you take a pi bond to act as the nucleophile, you pick the carbon. Was it carbon 1 or 2 here when I number? 3, 4, 5, 6, 7. Well, if 1 is the number, we have a 7-membered ring. If 2 attacks 7, we have a 6-membered ring. We know that is our goal, is the 6-membered ring. So you get to pick that 2 is the one that attacks 7. So let's include those numbers. 2, 3, 4, 5, 6, 7. That's our 6-membered ring. 1 is not part of the ring. It's left out. Poor 1. Okay. Because 1 did not make the new bond, it gets to be the carbocation. This is great review for that alkene section, right? And between 5 and 6, we had a pi bond. Carbon 5 has a methyl still. We're good to go. We're almost there. We just have to do our last elimination. So take off the H, leave behind a pi bond, and voila, we can do arrow pushing for a biochemical process. Even with enzymes, we can't let them intimidate us into trying to explain the arrow direction of electron flow. Okay, so what do you need to be able to do with terpenes? I have this list for this section simply because it opens up a big, tempting rabbit hole to go down for each of these categories. Stop at this level because, like I said, we're just showing this gentle overlap of organic with biochemistry. You will dive deeper later. So what do you need to do? You want to identify terpenes. When you know something's a terpene, prove it by circling the isoprene units and acknowledging their head to tail and tail alignment. And then predict some simple, so I'm looking at this little checklist here, mechanisms like the one we just did involving the OPP leaving group. Steroids. Steroids are very interesting. We've looked at them before, and this Robinson annulation is a particularly useful way to synthetically access them. What makes something a steroid? actually a steroid is a lipid that is often described as a terpenoid. Oid has the suffix meaning like a terpene. Terpenoid lipid. So not a terpene, otherwise it'd be in the terpene section. They're terpene-like. It's because they were derived from terpenes, but somewhere along the way, the structure was modified enough to lose one of the fundamental pieces of the isoprene unit that no longer allow it to be called a terpene. Steroids have this other feature because it's a repeating pattern of the 6,6,6,5 fused ring systems. When you have ring system fused like this, the consequence, you can see it in this model. Like you can also draw them as chairs or puckered envelope conformation, but look, which gives you an idea of the 3D nature. They're very rigid and kind of planar, which kind of hints at what it's, when it would be useful for a particular function. So the ring system is fairly rigid and fairly flat. So what are steroids made from? They're all made from this interesting terpene called squalene. Famous terpene, squalene, because it's the origin of steroids. Very important terpene. Very big one. So knowing that squalene's a terpene, I want you to pause and prove it's a terpene. Circle all the isoprene units. How many isoprene units are there? How many? How many did you get? Hope you got 6. I'm going to do this one with you, but I'm going to be asking you that repeatedly for some others. So I always start at an end with a branch, the iso branch. In this case, they both have that, so you should be set no matter how you started. So let's circle. 3 for the iso, 4, 5. Here's the iso piece on this one, 4, 5. Here's our iso piece, 4, 5. And now look at this one. We're starting with the tail this time instead of the head. 5, 4 plus the 3 for the iso piece. And now we're starting with the tail here. Go there. Add that up, you get 6. Now notice also the orientation. These are head to tail. And these are head to head or tail to tail connection. So actually we don't have any head to head on here. Yeah, because this one's also, so it's tail, they're connected by tail to tail, and this is a head to tail again. And if I'm going to be really picky, since I'm reading this left to right, I'm going to say tail to head. Okay, so because you see the tail, then you see the head. Tail, head, and then what do we see here? Tail, head. Tail, tail, head, tail, head, tail, and we're done. Okay, so then starting with squalene, it interacts with an enzyme known as squalene. So it's an enzyme specifically for squalene. Epoxidase, what do you suppose it does? Yep, it takes squalene and it epoxidizes one of its pi bonds. We know that pi bonds, alkenes, can undergo epoxidation. It does it on this terminal one, this right here. This is now called squalene oxide. Still a terpene. Then an enzyme called squalene oxygenase comes along. Oxocyclase. What do we suppose that does? Lots of ring closing. These are arrows we can push. Look what happens. The epoxides open. That's what epoxides do. It's positioned to be more reactive. What can open epoxides? Any nucleophile. What nucleophiles are present? Pi bonds. Let's show that. Let's push the arrows. So you could start by saying, I know the epoxide is going to open, right? And I know I made a new bond. So look at, you could even kind of trace. It's stereoselective with the presence of the enzyme, but you can see that used to be the oxygen in the epoxide. And then we see these little feet here that are actually the head of the isoprene unit right there. So we know that this is where the new bond was made, right? So it attacked here and opened the epoxide to be on that carbon. So we can show this pi bond attacking there, and that would give us the right number of carbons. 1, 2, 3, 4, 5, 6 membered ring. That leaves this prone to an attack because it makes a carbocation. So what can attack a carbocation? Another nucleophile. So this will attack. So if it's going to attack, we have to make, and remember it's fused, it has to attack here. So it shares a side. That's what steroids have, a fused ring system. So it attacks there. You can count the carbons to confirm that does form a 6-membered ring. Then once again, this one, once it opens, it's going to leave behind a carbocation. And instead of drawing each intermediate structure, we're going to draw this all as one big cascade of arrows. And that's actually a mechanistic term, cascade arrow pushing. So this needs to attack. Figure out which carbon makes sense. You can pause for a second. Is it this one or that one? You might need to look at the structure. Okay, I hope you picked this one. Okay, that brings us to our last one. Predict the arrows. Where does it go? It needs to be fused. We need to make a 5-membered ring. How's that going to work? Okay, so let's count. So if you have 1, 2, 3, 4, 5, 6, that means this one is the carbocation. That one is the one that gets attacked. Attack. 1, 2, 3, 4, 5. So that's the carbon that bonds with it to make that 5-membered ring, right? And we end up getting this whole chain coming off. 1, 2, 3, 4, yeah. Okay, so give that a try. Redoing that. Why is this wrong? I have a problem here. 1, 2, 3, 4, 5. That puts the methyl at a different spot. Let's fix it. How might I avoid that mistake in the future? How about I go the other way? Attack. I know that this is this carbon here. That needs to be loose, not part of the ring. So 1, 2, 3, 4, 5. Attack that carbon. Fused to, that makes perfect sense because now it's a fused 5-membered ring. That releases this pi bond to attack one of these 2 carbons. So if I know I have this here, and if I look down at what's going on, I have a methyl sticking out. So I've got 1, 2, 3, 4, 5, 6. So that's got to attack that one if I'm going to have a 6-membered ring. 1, 2, 3, 4, 5, 6. Okay. Now what about this guy? If I attack this one, that's because it used to be the carbocation. If it was the carbocation, that means this one was the one that attacked. So 1, 2, 3, 4, 5, 6. That's going to attack this one. Finally, for our last 6-membered ring, this needs to attack. Actually, I'm going to pause for a second. For the last 6-membered ring, which way does the epoxide open? Who gets attacked? Let's call it A or B. Which carbon? Look at your structure here and see which one got attacked. Did you get your answer? Have you got A? How do you know it's A? Well, this piece is this piece, And there's a new bond right there. And there's our alcohol on B. So this is A, and that's B. So that means we attacked A. The other way you could find out is from a carbon count. 1, 2, 3, 4, 5, 6. This had to be our nucleophilic carbon because this was an electrophile. Got attacked. Had to open octet to get attacked by this one. So make sure all those arrows make sense. 6 had to make the bond because 5 was the carbocation that got filled by these arrows. If 5 was the carbocation that got filled by these arrows, then this one had to be, they had to connect here to make the 6-membered ring. 1, 2, 3, 4, 5, 6. And this one was the carbocation, which makes sense because this one got attacked here, right? And so on. So work your way through. Once we've made squalene oxide, we made lanasterol. Notice the ending. The all, esterol, cholesterol. It's the precursor to cholesterol. 25 more enzymatic steps we won't belabor. We're at cholesterol. Why is cholesterol such a momentous moment? Because every other steroid is derived from cholesterol. I want you to do another activity. We know that steroids, now cholesterol is a steroid. That means it's not a terpene. It's a terpenoid. So it came from a terpene, but somewhere along the way, with all those enzymatic steps, it can't be a terpene anymore. Why? See what changed. Try to find some of the isoprene units are still visible. Some are gone. So are destroyed. So prove that, okay? Other steroids to be aware of. The ones that play a role is sex hormones, testosterone, estrone. Now they look very different, but they have you can always spot a steroid with a 6-6-6-5 fused ring system. 6-6-6-5 fused ring system. The rest of the functional groups could be variable. Because they can have very variable functional groups, they have very different roles. So corticoid hormones, adrenal glands, they help regulate metabolic processes. 6-6-6-5, 6-6-6-5. Cortisone, aldosterone, glucose metabolism, sodium-potassium balance. I mean, very different functions, but likewise, on the other hand, probably related to its planar, sort of perfect shape to activate those functions. Another one, some of the bile acids, cholic acid, still a steroid. You can spot it with a 6. Oops. So what you want to do is look at something and say, is that a steroid, or does it just look similar to one? Or is it something else? How do I classify this molecule? 6-6-6-5, yep, we got a steroid. So although they may have similar structures, they clearly have very different functions. So we don't have a function that you have to connect completely to it, but draw steroids and at least the basic skeletal structure, the ring part from memory, and if you look at a molecule and it is a steroid, you'll be able to recognize it. I lied. This is not the steroids. It's not the last section. Vitamins are, of course. Okay. Vitamins are interesting. We all need them. But they're a very broad category. Okay, so you ready for a big definition? It's always fun. Organic compound. That's why we're here. Other than fat. Why are we excluding fat? We're not just excluding fat. Lots of others. Amino acids. Because those are organic as well. Peptides, also organic. Proteins. Or carbohydrates. Okay. What do those all have in common? They're part of our diet. So this is like the catch-all category. We can very easily describe carbohydrates, proteins, peptides, amino acids, and fats. But another necessary part of our diet is some of these other molecules that we put in the category vitamins. So these are required for normal metabolism. Now, the other feature that vitamins have in common is they must be obtained through diet or vitamin supplement, but they're not just naturally, they don't just naturally spring up through. So you do that best with a varied diet. Abbreviate through because we're running out of space. Okay, so some vitamins are lipids, some are not. We have this term lipophilic vitamins. All right, so we have two vitamins there. One's a lipid, one is not. Sorry, I actually don't have, I have only lipid ones there. I could tell you about one that's not. One that's not a lipid is vitamin C. These two are lipids because vitamin C, if you look at the structure of vitamin C, polar, water soluble. It can be passed through urine. Lipophilic vitamins are fat soluble. Fat soluble vitamins can overaccumulate and be stored, which is why you run the threat of overdosing on, over consuming them. So you have to monitor them. So in order for them to be lipids, they must be hydrophobic overall. Yes, you'll find some polar groups, but the vast majority of the compound must be hydrophobic. So yes, we have a polar bond there and a polar bond there, but look at the rest of it, it's pretty greasy. Same with vitamin A, only one polar group, the rest are not. These vitamins also have terpenes, isoprene units. See if you could find them. Why do we not call them terpenes? Because on their own, they're not 100% made of isoprene units only, like this benzene ring, clearly. But you want to find them. So you want to be able to identify when a vitamin's a lipid or not. And have fun identifying the isoprene units and check your work back with me. There's a lot of other practice problems like that out there in the book and our workshops. And they're pretty fun to do to help you kind of really get comfortable with navigating those structures. So I recommend practicing those. So go give this a try and see what numbers you come up with.